Hi everyone, I'm Daniel Köhn from the Institute of Geoscience at Christian-Albrechts-University Kiel. Welcome to my new course on the application of seismic full waveform inversion to synthetic and field data. In recent years, the waveform inversion has become a really successful tool for high-resolution characterization of the subsurface. Especially here in Kiel, we are focusing on the near-surface application of full waveform inversion. As part of the lectures on inverse problem theory, I already delivered a short introduction into seismic full waveform inversion. However, this course is now really focused on the application of waveform inversion in order to invert synthetic and field data. Okay, so let's start with a short look on the course syllabus. So first I begin with a short review of the theory of full waveform inversion and show a few synthetic and field data applications, just to get an idea what the general idea behind waveform inversion really is. Now the first part will be really short because we really want to focus on the application of waveform inversion. In part 2 we will focus on the seismic forward modeling aspect of the waveform inversion. So this is really crucial that you can accurately model the full information content of your recorded wave field in order to estimate high-resolution models of the subsurface. It's a really important part that you get this right. How can you really accurately model a seismic wave field? And I will go really deeply into the different aspects of the modeling code so that you can set all these parameters more or less correctly and what you should take into account to get really an accurate seismic forward modeled wave field. So again, a really crucially important part of the waveform inversion to get this correct. Part 3 is optional because unfortunately the semester is far too short. So with our waveform inversion code we can also apply seismic imaging in terms of the reverse time migration approach. So I've prepared some tutorials on that, but yeah, as I mentioned, unfortunately the semester is too short, so this will be an option that you can do, for example, at the end of the semester, but it's not crucial for the course itself. And finally, in part 4 we are dealing with the seismic full waveform inversion. Especially we want to invert synthetic and field data. So for the field data application I'm choosing every semester a different near-surface data set, and then we are trying to invert this data set. Yes, so again, the focus of this course is on the application, so part 2 to 4, and a little bit on the theory and introduction to waveform inversion. So next question that I typically get from the students is where can I download all the stuff that is related to this course? And I prepared a special homepage for the course here on my WordPress homepage. And here you can find actually all the details of the course. So we'll start with this short overview, which is essentially this video over here. And then I have these 2 lectures or 3 lectures on the theory of waveform inversion, application to synthetic data, and then some challenges in near-surface 2D SH full waveform inversion field data applications. After this short introduction into the theory and application of waveform inversion, we will dive deeper into the application aspect of the waveform inversion. So the waveform inversion is computationally quite intensive. Yes, we cannot run this on a student's laptop or a smaller desktop PC. You either need a workstation or a supercomputer. And because the Kiel University has a really nice computing center with a large supercomputer, we will use this supercomputer. So in this course you not only learn how to apply waveform inversion to field data, but you also learn the high performance computing aspects of this problem really well. So how you can run code on a supercomputer, how you're using the queuing system and stuff like that. So really important stuff that you can use not only for the waveform inversion, but for a lot of other high performance computing aspects, for example, also related to seismic data processing of really 3D data sets, for example. So first I will give a tutorial on how you can log into the supercomputer. That is not listed here. I will send a link to all the students at Kiel University because I obviously don't want that everyone can log into the supercomputer. Then I will give a tutorial on how to install our full waveform inversion code on the supercomputer. The code that we are using is the Denise Black edition code, which I developed as part of my PhD studies. So it's a really well developed code. I will talk about it a little bit later in more detail. So these are then more or less the computational aspects. So how do you run the code and how do you install the code on the supercomputer here, the NEC cluster at Kiel University. Then we are dealing with the seismic forward problem. So first I shortly review the governing equations of seismic wave propagation and how to solve them numerically using the finite difference method. So this is really a really short recap on how to do that. And then we are trying to model the seismic wave propagation in the so-called Mamouzi-2 model. So that is a really complex subsurface model used in the hydrocarbon exploration. So I have a really long video on that. And then in the next tutorial I explain all the modeling parameters and a nice Python IO Jupyter notebook that we can use to streamline a little bit the modeling process. Yeah, so we don't have to change 100,000 input files, but we can create these input files with this Jupyter notebook in a really nice way. This Jupyter notebook, by the way, was developed by Oleg Ovcharenko from KAUST, so the King Abdullah University. And yeah, it's a really nice addition to the Denise Black edition code. We will finish this section on how to solve the seismic forward problem with a small exercise entitled Model Your Own Stuff. So you have to change the model a little bit and then run it on the supercomputer. So I have an exercise here and 2 hint videos about that. Next we have this optional section, I will add this here as optional, regarding the seismic imaging aspect of the Denise Black edition code. So you can simply turn off and on a switch to change from seismic full waveform inversion to seismic imaging using a really nice method called reverse time migration. But as I mentioned before, unfortunately we have not the time to deal with this part of the lecture because the semester is far too short. So you can optionally watch this video and I will also give a short tutorial on this topic and also an exercise. So if you're interested in this topic, you can also work on that. And finally, the most important aspect of this lecture, and that is the seismic full waveform inversion itself. So I divided it into 2 parts. So first we are inverting a synthetic data set for the Mamouzi-2 model. That's quite insightful to get an idea what the advantage of waveform inversion is compared, for example, to first arrival travel time tomography. So first we invert simply the Mamouzi-2 data with a perfect data acquisition. So we will get a really high resolution model out of it and everything is perfect and it looks quite impressive. Yeah, so you will be really blown away by the result that you get from this first inversion run. Then I will discuss a little bit the inversion parameters. That is a little bit tricky because you can fine-tune all the inversions using these parameters. That's actually a quite short part because most of the parameters are defined here in the seismic forward problem. So here we have only to change some fine-tuning parameters for the waveform inversion, and for the most part we can actually use the default parameters. And in the last part of this section we will try to invert the Mamusi-2 data with, say, not so perfect or more realistic field data acquisition geometries. And as you will see, the inversion result will not look as impressive as in the first part over here. Yeah, so that's quite interesting to do. Actually, this will be some part of an exercise, I think, so that you can really play around a little bit with the different acquisition parameters. And in the final section we are dealing with the field data application of waveform inversion. So every year I will choose a different near-surface dataset that we acquired here in our working group. And for this year, actually it's not 2021 but 2022, I'm choosing the INOS SH dataset. So I will first give a short overview of how this dataset was actually acquired and what the aim of this dataset really was. Then we are dealing with the data pre-processing aspect of the waveform inversion, and for this part I have written a separate code called Birgit. And so first we are taking a look at the raw INOS SH data. And then we are dealing with the field data pre-processing that is required for the full waveform inversion. Yeah, so it's really easy to do this with this Birgit code. Yeah, so you only have to do some normalization and some transformations of the data, and it's actually quite easy to do. And finally, we will apply the waveform inversion to this field data set. So first I want to discuss the estimation of an initial model, which is a quite crucial aspect of the waveform inversion. So the success of the waveform inversion really depends on the estimation of an initial model. In this case of the INOS field data set, the initial model can be really quite easy. That's the reason why I've chosen this data set for this first round of this waveform inversion course. Okay, after we have estimated an initial model and seen, okay, this initial model is quite useful for the waveform inversion, we will use this model as a starting model for the first full waveform inversion run of the INOS field data set. And after that we will tweak a little bit the inversion parameters in order to improve the resolution of the subsurface model. And then, maybe that's also an exercise, we will try to apply a random objective waveform inversion. That is a quite novel waveform inversion approach which randomly changes the objective function. And if we get enough students for this course, we can estimate average models and standard deviations of these different models, so we can get an idea how accurate the waveform inversion actually works. Yes, we get, for example, an S-wave velocity model of the subsurface, then estimate an average S-wave velocity model from different random objective waveform inversion runs, and then can also estimate standard deviations of the S-wave velocity variations. So this is really an interesting approach, and I'm really looking forward to see what results we can get out of this data set. Beside this detailed description of the course on my WordPress homepage, I've also created an OLAT page restricted to the students at Kiel University. So you can find it in OLAT called NGP2E Seismic Waveform Inversion. And when you start the course, you get a lot of details, especially how you can log into the supercomputer. There's also a forum where you can ask questions. You can also send me an email. There's a calendar with the suggested course syllabus. So when we talk about different topics, and there will be a news section where I post news on a regular basis so that you can really work on different aspects of the waveform inversion and in which order you should do that actually. The students who watched my other classes already know how extensively I use the Open OLAT system, so don't forget to subscribe to the OLAT so that you can get news on a regular basis. So typically I send news every week about the current topic of the course. As you have seen on my homepage, I will upload all the tutorial videos to YouTube. So they are not only accessible to all the students of Kiel University, but to everyone. So if you have access to a supercomputer or a workstation, then you can reproduce more or less all these tutorials. You might have to change some compiler options specifically for your machine, and also maybe some queuing files. But overall, these tutorials should also work on your computer. What might be also useful is to use my list of internet resources related to seismic forward modeling and full waveform inversion. Yeah, so I created a quite long list here with different topics: seismic modeling, full waveform inversion, seismic data processing and imaging, finite elements, programming and numerical libraries, LaTeX, visualization, geodynamics, then physics, theory of seismic waves, fluid dynamics, and then a bit of astronomy, nonlinear dynamics, mathematics, and other stuff. So you can look through this list of links and see, first of all, if they are working. So if they are not working, please send me an email. And maybe some of these links are quite useful, especially for this course related to seismic modeling and full waveform inversion. Let's cover a few important references. Unfortunately, I had not the time to actually prepare some lecture notes for this series of lectures. Fortunately, a lot of PhD students, postdocs, and professors have invested a lot of time to prepare really nice lecture notes. So let's start with the lecture notes on full waveform inversion by Romain Brossier and Jean Verrieux. They're already 10 years old, but still valid. So they're actually focusing on frequency domain modeling and seismic full waveform inversion. So I'm simply copying the link and add this link into my browser. And here you can see now all the lecture notes as PDFs and also the oral presentations as PDF. So this is my recommendation number 1. Recommendation number 2 is this lecture notes on geophysical imaging by Ludovic Métivier. So that is a really recent lecture that he gave in the last autumn, I think. So let's look at that. So this is actually his homepage, and under the section lecture notes and slides you can see here lecture notes that you can download and also slides for all of the sessions. There's also a nice Fortran code that you can use for seismic forward modeling. And he has also some video lectures here, especially regarding the topic optimal transport distance for seismic imaging using waveform inversion. Yeah, so there are a few videos about that. Finally, I would recommend this PhD thesis by André Kurzmann. So it's actually not a lecture note, but he has written an extensive PhD thesis regarding acoustic and viscoacoustic modeling for 2D and 3D media. And in this thesis he quite extensively describes the seismic forward problem as well as the inverse problem and how to solve that. And beside the theory, he also shows a few nice synthetic data examples. So these are my recommendations for lecture notes on full waveform inversion. A little bit more general recommendation is this book Numerical Optimization by Notchedal and Wright. I referred here to the version from 1992, but I think there's also a version from 2006, maybe even a newer one. And this focuses not on full waveform inversion, but a very important part of the waveform inversion, and that is the numerical optimization. Yeah, so if you want to do anything regarding numerical optimization, so it doesn't have to be related to waveform inversion, you will most likely find a really useful algorithm in this book. Yeah, so it's covering local, I think also global optimization approaches, step length estimations, so all the problems that are typically related to numerical optimization. So I really highly recommend this book, and I think you can find it also in our library. Okay, so these are my typical recommendations for lecture notes and books. Yeah, and then some further internet resources. So I was a little bit lazy. I actually referred here to the homepage of Romain Brossier, who is actually one of the few specialists about full waveform inversion and seismic imaging. So he extensively worked on this topic since his PhD thesis in 2009. So actually we worked on the same topic at around the same time. Yeah, and the interesting part on his homepage, okay, I think there are also other interesting parts, but the most interesting parts for me are here the publication lists, also the extended abstracts and the thesis list. So I can also highly recommend to read his PhD thesis, even though some parts are in French. Doesn't really matter because you can understand equations anyway, and I think he also included a few of his English written papers. So I highly recommend also to read this PhD thesis. Okay, so this would be my first recommendation. Then I refer to the homepage of Ludovic Métivier. Okay, I have shown this already before. So beside his nice lecture notes and video lectures, you can also see a publication list, PhD and HDR thesis, and then also here some open source software, which I will discuss later in this overview. And both of them are actually the heads of the SciScope 2 consortium. So that is an industry consortium focusing on high-resolution seismic imaging by full waveform inversion. And I recommend also this homepage, especially here the documents section, where you can also find publications, extended abstracts. Then really nice here this PhD dissertation list. Yeah, so there are a lot of really interesting PhD theses that you can download here. And yeah, then also the lecture I already referred to. They also created recently a really nice 3D model of a subduction zone. So that can be used actually as a benchmark for 3D seismic waveform inversion. So that's also quite interesting. And finally, I recommend the homepage of Stefano Perto, who is actually also the head of the SciScope consortium. And yeah, his homepage is a little bit broken, but you can also find here a nice publication list on recent studies regarding full waveform inversion. And then also a nice presentation about teaching. So full waveform inversion tutorial. Yeah, there's also a PDF file and a link to a video lecture. Yeah, so these are the most important, I think, internet resources that you can use regarding full waveform inversion and also recent advances in full waveform inversion. So this covers most of the internet resources that you can use for this course. Students are also always eager to invest a lot of money into books. So, you know, academic books are quite expensive. So I will just recommend two of them, and perhaps you can find them in the university library or maybe have access through the internet. So the first book is called Computational Seismology and was written by Heiner Igel. So the focus of this book is not on seismic full waveform inversion, but on the seismic forward modeling problem. So how can you solve the seismic forward problem using finite differences, spectral elements, Fourier methods and stuff like that. So it's really useful to get an insight on how you solve the forward problem, because as I mentioned now hundreds of times, the seismic forward problem is the most important part of the waveform inversion. Now, speaking of solving the seismic forward problem, I've created a whole course on numerical modeling of seismic waves, which covers all the important aspects, so from the theory to programming to the seismic modeling itself. And if you're interested, I have linked the course homepage to this course over here. There are also YouTube videos. Unfortunately, they are currently only in German. And if you're located at Kiel University, you can actually take part in this course and also get some credit points for that. So really interesting course and a really nice supplement for the waveform inversion. But I should mention it's not really necessary to hear this course in order to understand the waveform inversion. Then I want to recommend a book on full seismic waveform modeling and inversion, written by Andreas Fichtner, who is one of the experts on seismic modeling and waveform inversion, especially using spectral element codes. So he has written a spectral element code as part of his PhD thesis, and graduated at around the same time that I have graduated with my finite difference waveform inversion code. So really nice book on seismic modeling and also waveform inversion. What is not so nice about this book is the price point. So the ebook costs around 160 euros and the hard and soft covers over 200 euros. So I would highly recommend that you check your local university library if this book is available. If you have a lot of money, you could buy it, but actually I would not invest 200 euros for a book. And not even this nice book by Andreas Fichtner, but more generally any book. So it's a little bit above my typical price suggestions for books. Next, let's discuss the waveform inversion software that we will use in this course. And of course, we will use my own software that I developed as part of my PhD thesis. So actually, I developed now a package of software related to waveform inversion, and also to develop initial models for the waveform inversion using first arrival travel time tomography, and also a pre-processing package to pre-process data specifically for waveform inversion. Yeah, so we have this bunch of code packages. So the first one is Reizel, which is a 2D first arrival travel time tomography code. Then we have the time domain waveform inversion code called the Nice Black Edition. We also have developed a frequency domain code called Germain, which is currently in the alpha stadium, so it's not really working that well. It works for synthetic data, but field data application is more long-term aspect of this code, so it's not really working and we will not use it in this course. Then we have a first arrival travel time and full waveform inversion pre- and post-processing package called Birgit, where we can easily import the field data and apply all the processing steps required for the waveform inversion. One nice aspect of these codes is that they are open source, so you can easily download them from my GitHub homepage. And my general recommendation for software development and science is that they should always be open source. So first of all, this is important to reproduce results of other people, but it also builds a really nice community of guys who contributing different aspects to the code. At this point, I want to thank all the developers and contributors to these codes. Some have reported some essential bugs, and others have rewritten really large parts of the code in order to improve the performance and also add new aspects to the waveform inversion and the forward modeling. So big shout out to all these guys. You're really fantastic and have contributed a lot to these software packages. More generally, I also want to thank the growing list of contributors to the full waveform inversion research at Kiel University. So these are not only geophysicists, but come from really different fields of research, like archaeology or geography. So these people really helped to develop a robust workflow for near-surface full waveform inversion, not only by code development, improving the robustness of the waveform inversion workflow, but also by methods of ground truthing, so that we can really check the resolution that we can achieve by waveform inversion with the true situation in the subsurface. And in the short introduction series on waveform inversion, I will show some of the really impressive results that we could achieve here at Kiel University. Now, a few slides ago, I mentioned that my philosophy is that scientific software and data should be open source in order to ensure that research results are reproducible and replicable. And therefore, we will not only use our open source waveform inversion codes, but also use Python as an open source ecosystem for the data preprocessing and visualization. Yeah, so my data preprocessing code is basically programmed in Python, and we will also use this for visualization of the final subsurface model that we estimated by waveform inversion. So I highly recommend to use Python because you have really a large universe as it's shown here. So this is the Python-centric universe. So in the center you have Python, and in the first orbit you have NumPy, which delivers data structures similar to MATLAB, for example. Then you have Jupyter notebooks, which are a really nice way to combine programming with lecture notes and videos. Really nice aspect of the Python universe that I extensively use for my lectures. Then you have optimization tools like Numba and Cython to really use multi-core performance of computers to improve really the performance of your codes. Especially I want to highlight here Numba, which I extensively use in my lectures. Then you have Matplotlib for visualization, also Bokeh. SciPy is really essential if you want to do some pre-processing. For example, it contains a whole library regarding to filters, so in 2D or 3D filters, for which you have to pay a lot of money actually if you want to use them in MATLAB, but in Python these packages are free. So that's a really nice aspect of Python. And then when you go into the higher orbits of the Python-centric universe, you see here other more specific packages like SymPy for symbolic math. And then also here AstroPy for astrophysics, or SunPy for solar physics, and then neuronal network stuff. And yeah, so if you're trying to program some stuff in Python, chances are really high that some other guy has already programmed something similar. So you should always check the internet first if there's something available related or similar to your problem that you can use for your own research. So really powerful package that you can use. And as I mentioned before, it's all open source, so you can use it without any extra fees. In order to use Python, you can either install Python itself and then try to install all the packages that you want to use. However, this is not really a good approach because a lot of packages are incompatible, especially if you're using different versions. So what I highly recommend is that you install the Anaconda distribution, which contains most of the important libraries by itself, and it's also quite easy to install other packages with this Anaconda distribution. So I've given here a link. You only have to download the code here with this download button and then install it on your computer. It can be Windows, it can be Apple, or it can be Linux. So it's available for all major systems. And if you want to refresh all your knowledge regarding Python and Jupyter notebooks, I've linked some tutorials that I have used in my differential equations in the Earth system class. Yeah, so if you're following this link, there are some Python tutorials that are quite useful. Also this NumPy for MATLAB users introduction and cheat sheet. So if you're coming from MATLAB, this might be quite useful. And then also some lecture notes and other stuff and videos, for example, regarding Python, NumPy, SciPy, and all the other nice stuff. I highly recommend one tutorial, and that is a series of tutorial notebooks written by Lorena Barber. So if you have more or less no Python knowledge, which is highly unlikely at this stage in your master studies, then I highly recommend to work through these Jupyter notebooks. Yeah, so they're starting really simple with the basic data structures, for example, in Python and how to program some stuff. And then it gets quite advanced. So there's also some stuff here with vector spaces, transformation of matrices, how to estimate eigenvectors. And then also stuff related to Fourier transform. And also deep learning, which is currently here work in progress. So that's also a nice resource regarding Python. And finally, there is an about 2-hour long tutorial video by myself that I recorded for some lecture. Unfortunately, it's only in German, but the notebook is in English, at least I think so. So you can use also this tutorial video to refresh your knowledge on Python and Jupyter notebooks. Now I mentioned that the waveform inversion is computationally quite expensive, simply because you have to model the full waveform information of the recorded wave field. So you have to do a lot of forward modeling. And therefore we are required to use high performance computing. So you cannot do this course on your laptop or desktop computer. If you are a student at Kiel University, you can use the NEC cluster in our computing center. So this is a really powerful high-performance computer combining different hardware components. So we have a scalar NEC HPC Linux cluster, then we have a GPU cluster and a vector computer. So slightly different architectures that can be used for supercomputing. And we have a lot of computational resources that we can use for this course. For example, here almost 15,000 Intel Xeon x86-64 cores. Then we have 5,120 NVIDIA CUDA cores. That sounds like a lot of stuff, but actually I think it's only 2 or 3 graphics cards or something like that. And then we have additionally 512 NEC SX vector cores, which unfortunately we cannot use yet because the Denise Black edition code is not really vectorized. So we have to rely basically on these 15,000 cores. But I think for this course this should be actually enough, because even the field data application doesn't require that many cores. I also added a link to the NEC cluster at Kiel University homepage. where you can find more details regarding the hardware, the software, the documentation, and really important, how to access the NEC cluster. So you have to fill out a special form to get access to this cluster. I will describe this in more detail on the OpenOLAT homepage. If you're interested in more details on how to use the cluster, there's also high-performance computing courses and materials that I think are delivered every semester. So they are giving an introduction in English and in German regarding high-performance computing and how to use the cluster. However, I will also give a few tutorials on how to use this cluster, specifically for waveform inversion and how to install all the software packages that are required for this course. With this short introduction into high-performance computing at Kiel University, I conclude this overview of this course regarding the application of Seismic Full Waveform Inversion. I hope you will enjoy this course, learn a lot of new stuff, and I see you in the next tutorial. Bye for now.